Hello, we are Clearview Consultants. I'd like to thank you all for coming to our presentation today. I'm Kyle Gustafson. I'm the project manager for our team.
I'm Keith Balhan. I'm an instrumental engineer.
Corey Miller. I'm the design specialist.
Shingus Kanapian, the regulations specialist.
And I'm Alec Thomas, the chemistry specialist.
The project under discussion today is to be entered in the WEF Tech competition, and it is to design modifications to the 75th Street wastewater treatment facility in Boulder, Colorado, in order to meet new state regulations for arsenic concentrations in effluent. We felt it would be appropriate to first discuss the new regulations that the plant will have to meet very soon. So the new state regulations come from the treatment plant operating under a discharge permit, which is from the Colorado Department of Public Health and the Environment's Division of Water Quality. Under this new regulation, under this discharge permit, a new regulation of arsenic must be met by June 1st of this year, which is 0.023 micrograms per liter of its effluent before discharge into Boulder Creek. Boulder Creek is considered a Class 1 waterway. So this regulation has been determined by the possible health effects that could be associated with consuming both fish and drinking water that are consumed downstream in Boulder Creek from the after the wastewater treatment facility. So we at Clearview Consultants are proposing a design that will cost-effectively and efficiently remove the arsenic from the effluent stream of the wastewater treatment plant in order to meet new state regulations.
So I'm going to talk about the wastewater treatment facility overview of the water treatment. This is a pretty simple diagram of their treatment process. They utilize primary conventional treatment through clarifiers. They also have an activated sludge treatment process that consists of a nitrogen removal process with an additional aeration polishing step. Finally, they utilize UV disinfection, which was recently introduced in the fall of 2012. It's important to note that they still have the chlorination, dechlorination as backup in case the UV fails. Solids are removed from the clarifiers, indicated by the red lines, and waste activated sludge. This is sent to the mesophilic anaerobic digesters, which is dewatered by centrifugation. These are considered Class B solids and are used for land application. These are the various treatment options that, through literature, we found to be the most efficient at removing arsenic. It's important to note also that some of these are primarily or really only used for drinking water treatment plants and not wastewater. So that's a consideration that we're definitely taking into account. Let Keith now talk about the biological treatment process.
Thank you. Biological treatment doesn't necessarily take the arsenic out of solution. However, it does fill an important niche in most treatment options that we have researched. What it does is it oxidizes the arsenite, which is arsenic 3+, to arsenate, which is arsenic 5+. This is beneficial in many levels. First, arsenite is more toxic, about 60 times more toxic than arsenate. Second, arsenate is more reactive than arsenite, so it's easier to remove and it's easier to treat. And a lot of the treatment methods that we have looked up require that it be arsenic 5+. So biological treatment fills this niche. Here's a graph showing the effectiveness of biological treatment. The top two lines are controls that they didn't add any activated sludge. However, you can see that the arsenite was reduced to almost no to very low concentrations of itself, and arsenate was converted almost 100%.
And the arsenic is also can be removed by the adsorption process. The process which removes the arsenic by attaching it onto the surface of the media. So, and some of the advantages to this process include high arsenic removal rate and predictable performances, and it's easy to implement and operate this technology. And the disadvantages to this technology or this process is that the absorption is unlikely to meet the effluent limit of 0.02 micrograms per liter, and it is normally used for applications below 2 million gallons per day. And pre-treatments are required like oxidation and filtration. And there are final sorption sites on media which needs to be regenerated or replaced regularly. And some of the types of solvents used in the adsorption to treat arsenic are activated alumina and activated carbon and iron-based adsorptive medias. And the presence of suspended solids, organic solids, silica can cause falling of adsorptive medias. And absorption is more effective in removing arsenic 5 than arsenic 3. And increasing the rate of flow through the adsorption unit can decrease the absorption of contaminants.
Another promising treatment method that we have investigated has been a coagulation co-precipitation unit. This method is by far the most commonly used method for treating large quantities of arsenic-contaminated water in the United States. And is commonly used in drinking water, but various research that we have reviewed has shown that it is also very effective at removing arsenic in wastewater streams to relatively low concentrations. For an overview of this process, the wastewater stream is first rapidly mixed with a coagulant for arsenic. Ferric salts have proven to be very effective, ferric sulfate and ferric chloride. After the wastewater stream is rapidly mixed with ferric salts, the arsenate becomes destabilized, which allows it to coagulate into larger flocks of particles. These particles are then settled or clarified out of the liquid stream to separate the arsenic from the remaining treated liquid. This is a very appealing method for treatment of the wastewater treatment plant because it also aids in phosphorus removal. Phosphorus is a nutrient of concern within the wastewater treatment plant. And if we were to implement this treatment method, it could prevent the plant from undergoing any further modifications to meet future phosphorus regulations. It also has relatively low operating costs due to ferric salts being relatively inexpensive, and they are currently at use in the treatment plant for different processes. So here you can see a plot of the effects of adding ferric chloride into a arsenic-contaminated wastewater. And you can see that for a relatively small dosage of ferric chloride, you get a large decrease in arsenic concentrations. Here's a diagram of what a coagulation co-precipitation unit could look like if it was implemented in the wastewater treatment facility. You can notice a rapid mixing tank, which will mix the wastewater stream with the stream of ferric salts. We'll then move on to a lower energy flocculation unit, which will promote the growth of larger particles. These particles will then be removed from the liquid stream through a number of different processes, including filtration and settling. The treated water will then be moved on to further treatment or discharged into Bowling Creek. The solid stream will then move on to processing along with the other solids that are generated in the plant.
So, membrane filtration. A quick definition of membrane filtration is a vacuum or pressure-driven process, separation process of particulate matter. Here's a quick illustration of the different capacities of the various membranes we're going to be talking about. The only one not included on this graph is electrodialysis. As you can see, reverse osmosis removes the smallest particulate matter, and microfiltration is on the opposite end of that spectrum. So I'm going to talk about ultrafiltration and microfiltration. Basically, it's a pretty simple idea. It's essentially size exclusion. So basically, the pore size of the membrane will reject any particulates that are larger than the size of the membrane. Something interesting we found through our research is that membrane charge can play a significant role in arsenic removal. A study showed that membrane rejected particulate matter that were 1 to 2 orders of magnitude smaller than the membrane itself. This diagram sort of illustrates that. Now I'm going to let Corey talk about reverse osmosis, nanofiltration, and electrodialysis.
Thanks, Al. I'll start by mentioning reverse osmosis and nanofiltration. The process is very similar to microfiltration and ultrafiltration in the sense that it's a semi-permeable membrane, the only difference being that it utilizes high pressure to accomplish the same goals as the other two filtration processes. Our third filtration process here you can see is electrodialysis reversal. Electrodialysis reversal is the same type of membrane filtration that utilizes semi-permeable membranes, with the only exception that the membranes are oppositely charged, and the reversal happens in which the polarity of said membranes is reversed occasionally to increase efficiency and avoid fouling. So throughout our research, we have come up with the need for a combination of methods, since individual treatment strategies are unable to reach the new regulations for arsenic and effluent streams of the wastewater plant. So we have to get a little creative and come up with a combination of these methods. And further research will be done on these methods to come up with the best combination to remove arsenic down to the new regulation. These regulations, or these combinations will be based on cost effectiveness, efficiency of removal, and ease of implementation. And they will be weighted in a decision matrix that correlate directly with our design goals. As you can see, our design goals are to make sure we meet this regulation at a cost-effective plan without changing huge amounts of infrastructure. Now I'll turn it over to Keith, who will explain how we will make this happen.
So for quality control, we will have a self-evaluation where each individual does their work and makes sure it's to the highest quality for the group. Then we will have a peer evaluation. That individual will submit their work to the peers. They will review to make sure that they've covered all the bases. Then we will send it off to our project manager. He will compile everything and make sure that it is clear, concise, and up to par with the deliverables that need to be met. Once he's done that, we will have another team evaluation, and once that's complete, we will submit any deliverable that we have. For our sources, we will make sure to get all of them from peer-reviewed articles and our government-issued papers, federal and state level. We will also ask any questions to faculty members and our peers, anybody that could help us out. We understand that the Boulder Wastewater Treatment Facility is very busy, so we will limit our communication with them to only site-specific questions that can only be answered by people who work at the facility itself.
We at Clearview Consultants have determined a very extensive design schedule. A very simplified version of it here is showing our deliverables for both the class and for the WEF competition. It's important to note that our next set of deliverables will be the alternatives assessment due March 14th, which will further assess various treatment methods that we have outlined in this presentation so far to narrow down the selection to more feasible options. This will be followed by a 90% design report, which will include a comprehensive study of the treatment method we believe is most feasible for the wastewater treatment plant, as well as computer-aided designs and schematics of the system as implemented in the wastewater treatment plant. Using our schedule and a prorated billing rate for each of our members based on qualifications and specialties, we have determined a budget for each deliverable and for the overall cost of our consulting work. From this, we have come up with a total amount of hours, 556, worked by the group in total, as well as a total cost of $27,000.
Once again, I'd like to thank you all for coming out, especially the representative from WEF competition. And right now, I'd like to open up to any questions that you guys might have. And again, thank you very much.
Yes.
My first question comes in very well.
You're welcome.
So I would raise your fees, like as a frame of reference, maybe 10% of your construction cost would be engineering fees. So this is an $80 million project.
We base these billing rates. We base these billing rates taking into consideration that we are all entry-level engineers with slight increases on specialty work. So, just for a justification for where that value comes from.
I'll hire you. And then I just had a question about the ferric fluoride emissions. Do you have any other chemicals that you're going to look at? Because I know that Boulder wastewater treatment stuff isn't really looking to add too much more ferric with their EV system and Class B biosol.
Yes, there will be, for the co-precipitation coagulation unit, there are a number of different compounds that can be utilized as a destabilizing agent for particle formation. We mentioned the ones that have been used explicitly in different sources of research that have looked at arsenic removal using coagulation. So that's why we used ferric chloride as an example for that. But alum and different ferric salts, as well as other agents, can be implemented, and we will look into this. And we also look into what is actually leaving that unit, and if there's any post-treatment out of that unit that will be necessary to ensure that the UV unit will function properly and prevent fouling, then we will look into that also.
It's also important to note that in the research we found that alum is less effective at removing arsenic than ferric chloride. That's why we also chose it as our focus.
When it comes to the membrane treatment, are you guys able to identify any membranes that would be selective in capturing arsenic and not get clogged up by oleoductin?
Yeah, primarily all of the membrane research that we found